Chapter 2, Part 1, The Ones Ahead of Their Time. If Chapter 1 painted a wide-angle view of black holes as cosmic mysteries, then Chapter 2 brings you face-to-face with real-life heroes, the scientists who dared to stare into the abyss and say, "Yeah, I'll figure out what's in there." And as you probably know, the history of science never lacks drama, especially when it comes to ideas that sound crazier than fiction. Let's rewind to the 18th century. An English clergyman named John Michel, who happened to be obsessed with math, sat down with his calculations and proposed the idea of a dark star. He claimed that if a star were massive and dense enough, its gravity would be so strong that even light couldn't escape. Sounds logical, but at that time, the idea was treated like a pub joke. Who would believe that light, the fastest thing in the universe, could be pinned down? Unsurprisingly, Michel's theory faded into obscurity, only to be resurrected almost 2 centuries later. Fast forward to 1915, Albert Einstein bursts onto the stage like a rock star of science. With his general theory of relativity, he showed that gravity isn't just a pulling force but the bending of spacetime itself. Think of the universe as a stretchy mattress. The heavier the object, the deeper the dent. A black hole. That's where the mattress caves in so much it basically rips. But here's the twist. Einstein himself didn't believe black holes were real. He thought they were too extreme to exist in reality. Pretty ironic, huh? The father of the theory disowned his own cosmic baby, while the kids, who came later, worked tirelessly to prove it existed. Enter Karl Schwarzschild, a German physicist and soldier in World War I, who solved one of Einstein's nastiest equations and delivered the first mathematical description of a black hole. He did it while literally on the battlefield, surrounded by bombs and chaos, and mailed his results to Einstein. You'd expect Einstein to be thrilled, right? Nope. He just shrugged. Cool math, but the universe probably doesn't work like that. A brutal brush-off, leaving Schwarzschild as one of science's unsung heroes. The stories of these pioneers reveal a truth. Black holes weren't just a test of physics, they were a test of courage. To believe in them was to admit that the universe isn't gentle at all. It can create places where even light gets swallowed whole. And to accept that, you had to be just a little bit crazy. In the next part, we'll meet the minds who turned crazy ideas into scientific evidence, not just scribbling equations, but aiming telescopes at the sky in search of these invisible cosmic beasts. Chapter 2, Part 2, The Hunters of Invisible Monsters. After Einstein and Schwarzschild, the 20th century welcomed a new generation of scientists, people who weren't afraid to dive headfirst into the forbidden zone of the cosmos to hunt for real evidence of black holes. And if you think they just sat in labs scribbling equations, think again. They were more like hunters, except instead of stalking animals in the forest, they were stalking invisible monsters in space. One of the most prominent figures was John Wheeler, the man who coined the term black hole in 1967. Before that, black holes went by painfully dull names like gravitationally collapsed star. Imagine trying to hype up a mystery of the universe with a phrase that sounds like homework. Wheeler cut through the noise. Black hole. Short, eerie, dramatic, instantly unforgettable. Thanks to him, the world had a name that hit like a drumbeat. Meanwhile, the hunt for evidence was in full swing. As I mentioned back in Chapter 1, the star system Cygnus X1 became the first serious black hole candidate. In the 1960s, 70s, with satellites and X-ray telescopes finally in play, scientists noticed one of the stars in the system was being tugged violently by an invisible companion while blasting out intense X-rays, the calling card of matter being torn apart and devoured by a black hole. Fun fact, Stephen Hawking once bet that Cygnus X1 was not a black hole, only to later admit he'd lost the wager. Goes to show, even the brightest minds sometimes bet on the wrong horse. Speaking of Hawking, you can't skip him in this story. He turned black holes from a dry physics concept into a cultural icon. With his wild hair, mischievous smile, and razor-sharp mind, Hawking didn't just study black holes, he told their story. Thanks to him, the world learned about Hawking radiation, the idea that black holes aren't completely black, but can emit energy and slowly evaporate. In simpler terms, black holes aren't immortal. They can die of old age. A plot twist that had both scientists and the public cheering. From the 1970s onward, the hunters kept gathering clues. Tracking stars orbiting the center of the Milky Way were the supermassive black hole Sagittarius A/lurks. And of course, the historic moment in 2019 when humanity saw the first ever image of a black hole, M87's glowing cosmic donut. Each discovery was like carving a cut in the darkness, sketching the outline of a beast once thought to live only in theory. This generation of scientists turned black holes from fairy tales of physics into undeniable reality. And through their work, humanity learned not just to fear the dark, but to touch it with science. In the next part, we'll dive into the intellectual revolution black holes sparked, how they forced us to rethink time, space, and even the very fabric of reality itself. Chapter 2, Part 3, When Time and Space Get Twisted. If black holes were nothing more than cosmic vacuum cleaners, the story would have stopped at scary but boring. What makes black holes true A-listers in science is how they force us to redefine concepts we thought we understood: time, space, and even reality itself. Let's go back to Einstein. According to general relativity, gravity isn't just a pulling force, it's the bending of space-time. The heavier the object, the stronger the bend. Now, with black holes, these mass monsters, the bend doesn't just make a dent in the cosmic mattress, it rips the thing right open. This means that in and around black holes, time and space stop behaving the way we know them. Take this example. If you flew near a black hole, your watch would tick slower compared to someone far away. This is called gravitational time dilation. In Interstellar, when the characters spend a few hours near a black hole only to return and find decades have passed on Earth, that's not pure sci-fi nonsense. It's actually a brilliant dramatization of what Einstein predicted. Black holes don't just bend space, they bend audience emotions too. Space doesn't fare any better. As you approach the event horizon, the coordinates we use to describe the universe start to fall apart. You could think of a black hole as a lawless zone of physics. All the familiar rules collapse. Distances can't be measured with rulers, time won't flow in neat ticks of a clock. It's a realm where the logic we've trusted all along just walks out the door. The miracle, though, is that from these paradoxes, science finds opportunity. Black holes are the battleground where two great theories, relativity and quantum mechanics, are forced to clash. One side says space-time is smooth and continuous. The other smirks. Sorry, but on the tiniest scales, it's a rave party of chaos. Thus, black holes become the arena where humanity hopes to discover the theory of everything, the ultimate cheat code for the universe. So yes, black holes are not just light-swallowing beasts. They're the greatest natural laboratories ever, hiding the universe's source code. And if one day humanity truly cracks their secrets, we may not only understand the cosmos better, but also ourselves. In the next part, we'll explore the bold hypotheses about information in black holes and why it triggered one of the fiercest debates in the history of modern science. Chapter 2, Part 4, The Black Hole Information Paradox. If you thought black holes were only headaches because they swallow light, welcome to the biggest drama in modern physics, the black hole information paradox. This is where scientists feel like slamming the table, or their heads, because it touches one of the most sacred principles in science. Information can never be destroyed. In physics, information isn't your crush leaving you on read. It's the data that describes the state of a system. For example, if you have a glass of water, the information includes its temperature, pressure, number of molecules, and so on. Even if the glass shatters, that information is preserved somewhere in the universe. That's the golden rule. But black holes, they're the naughty rebels who break the rules. When matter falls into a black hole, it crosses the event horizon and vanishes without a trace. All information about it, its density, composition, shape, seems to be erased. This drives physicists nuts, because if information truly disappears, the entire foundation of quantum mechanics, which relies on information conservation, collapses. Stephen Hawking lit the fuse for this debate. In the 1970s, he announced that black holes aren't completely black. They emit what we now call Hawking radiation. Over time, a black hole would evaporate, and disappear. Sounds cool, but here's the tragedy. When the black hole dies, all the information it ever swallowed dies with it. Suddenly, Hawking went from genius hero to supervillain in the eyes of quantum physicists. From then on, the scientific community launched into a decades-long shouting match. One camp said, "The info is gone, deal with it." The other argued, "No, the info is encoded somewhere at the event horizon." Some even proposed the holographic principle, the idea that all the information inside a black hole is stored as a kind of 3D projection on the surface of the event horizon, much like how a CD stores music. Mind-bending and artsy. This turned the black hole into the ultimate cosmic hard drive. To this day, the paradox remains unsolved. But one thing is certain. It has made black holes the center of fiery debates, forcing scientists to dig deeper in the quest for a unified theory of the universe. In the next part, the finale of Chapter 2, we'll reflect on the legacy of these debates and why black holes have become the toughest teacher, yet the most important one in humanity's journey to conquer knowledge. Chapter 2, Part 5, The Legacy of the Debates. And so, throughout Chapter 2, we've traveled from the pioneers who dreamed of dark stars to the hunters of invisible monsters like Wheeler and Hawking, and finally drowned ourselves in fiery clashes over the information paradox. The most fascinating part is this. Even without a definitive answer, these debates themselves have become the greatest legacy black holes left for humanity. First of all, black holes prove that science isn't a walk through a rose garden. It's a battleground of sweat and tears where scientists place bets, argue, and even openly roast one another. Yet that's exactly how knowledge pushes forward. Without Hawking boldly dropping his controversial idea, would we have ever considered black holes evaporating? Without those who stubbornly defended information conservation, would the holographic principle ever have been born? It turns out, scientific truth doesn't always grow from consensus. It often sprouts from conflict. Second, black holes transformed physics into a story that captivates the public. What once sounded like a nerdy fairy tale is now everywhere. Movies, novels, internet memes, and coffee shop chatter. You may never have solved an Einstein equation, but you've almost certainly heard the words black hole. It has become a symbol of the infinite, the mysterious, the all-consuming, and in doing so, it has accidentally pulled millions closer to science. Finally, black holes remind us that the universe is anything but predictable. Each answer births dozens of new questions. Today, we can photograph black holes, measure the orbits of stars around them, calculate the radiation emitted from their event horizons. But tomorrow, a new theory might flip the table and rewrite everything we thought we knew. And that's the beauty of science. It never sits still, never stops challenging us, never stops making us look up at the sky and wonder, what's next? Closing Chapter 2, we see that black holes are not just physical phenomena. They're main characters in humanity's intellectual journey. They teach us that sometimes, to understand the universe, we must accept inconvenience, contradictions, and mysteries without solutions. In Chapter 3, we'll shift gears, exploring the practical ways black holes might influence humanity's future, from space exploration to harnessing black hole energy. If black holes are monsters, could we one day turn them into allies?